Okay, in this lesson we're going to be discussing a thing called the chain rule. And chain rule because think functions linked with functions, and not simply by adding multiple functions to each other. In this case we mean functions of functions. So think f of g of x or f of g of x, right? Either way. But point being, functions in functions. So for example, this is something that we can easily differentiate. And oh, by the way, I should say to you that I'm following the PDF that I posted directly next to the video. These things we could do without the chain rule. For example, the derivative of x squared plus 1, hopefully you come up with already while I'm saying this, is 2x. So another way of writing that, just to really flesh that out, is in this particular one, dy dx equals 2x. And think about what this means. I know a lot of times it's just like, tell me how to do it, but in calculus, it's really important that you understand what the notation is doing. And the more you understand that, the easier things will be later. You know, it's like somebody teaching you to play guitar or something, and you figure out a way to get a C major. You figure out a way to put your fingers into a C major, and somebody comes up to you who's been playing guitar 10 years and they said, actually it's a little easier if you do it this way. And they have a reason for that, because you'll be able to more quickly change from one chord shape to another or whatever. And it's the kind of detail you just don't want to learn the first time you see it. You just think, listen, I already have this way of doing it. I kind of ignore the whatever. In this case, you know, the same deal is true in calculus. If I can offer you some advice as someone who's experienced with it, it's that the notation means so much. It's not just there to serve to hold a place on the side of an equation. What this means is the change in y with respect to x. And I know you've heard that 15,000 times, but think with respect to. What does that mean? Well, it means tell me how much y changes when x changes by a little bit too. So imagine a very small change in x. How does that affect y? Well, in this case, the y value goes up 2 times the amount of the x value that you're on. And that's because this particular one is parabolic. My intercept is a little screwed up there. But as you go further here, the y value changes. If you move the x value over a little bit, say from here to here, the y value will go up 2 times whatever the x value is that you're on. So point being, it's the change in y when x changes by a certain amount. Okay. So I think we could also easily take the derivative of sine, hopefully you know what that is, and then take the derivative of 3x plus 2. However, the list over here is functions of functions. This thing would be, instead of just the derivative of x squared plus 1, it's now x squared plus 1, but then the root's being taken up. And you might think to yourself, oh, okay, great, I'll just make it x squared plus 1 raised to the 1/2. The problem is we've never dealt with a function behind my hand here. We've only dealt with x to the half, or potentially 5x to the half, where we just said, okay, the 5 to the half, that's square root of 5, and then you dealt with x to the half. We certainly haven't dealt with any kind of complicated function raised to the half power. Similarly here, this one might look like, oh, well, what do you mean? That's no big deal. Well, this is actually a function of a function as well, because there's a linear function, 6x, and then you're taking sine of that value. And no, the answer is not cos 6x. It's close, but it's not quite cosine 6x. And then this one down here, this is very similar to the one here. It's, instead of just being x to the 5th, it's 3x plus 2 to the 5th. And the reason, if you're like, well, why can't we just use the old rules? Well, there's 2 things happening to x. X changes based on this linear function. When you change x, that's going to bump y up 3 times whatever change you made in x. But then also, it gets added to it and then taken to the 5th power. This 5th power causes y to change differently than this 3x plus 2 does. So we've got multiple changes that are happening to the initial input x that causes dy dx to be a little bit more confusing than what you might see with things on this list. Okay, so we're going to develop a process by which we can differentiate functions of functions. So the major goal here is if we have, let's say, k of x is equal to f of g of x, what is k prime? And if you're thinking, where the heck did that come from? Remember that, for example, the one I just erased, I think it was this. This would serve as g. G of x would be x squared plus 1. And f of x would be square root of x. And if you're thinking to yourself, didn't you leave off the x squared plus 1 inside here? No, because f takes the root after g does its thing in this form. You may need a second to digest that. Okay, so our goal is to find k prime. I'm not going to do a rigorous proof. I think it's more important for me to make an argument as to why this thing is the way it is. If you wanted to look at the proof, look in your book, talk to me, email me, and I'm happy to do a proof with you. So what I'm going to do now is compare, I'm going to actually use this function, y equals 3x plus 1 squared. And I'm going to accomplish finding its derivative in two different ways. First is simply by expansion. So if you rewrite y and expand it, you'll get 9x squared plus 6x plus 1. That's just good old FOIL, right? Now, remember, we've written a lot like y prime, but for this specific topic, and honestly, overall, I think it's much more descriptive and stronger notation to write it as dy dx. Again, that's the rate of change of y with respect to x. So we get 18x plus 6, and of course the derivative of 1 is 0. Now, I'm going to look at this as though, so let's just have y equal to 3x plus 1 squared. Let's just say you said, okay, well, listen, I don't know anything about this chain rule business. What I do know is when I see a power, I do one of these jobs where I multiply that thing by the power, and then I drop the power down 1. Well, we know that this works. This over here is fact, right? We know we can expand the thing out, and we know how to take the derivative term by term, and we know we're allowed to break them up and do the sums of different terms. So that's the derivative, is 18x plus 6. This thing, however, says, and I'll put this in a different color, this is 6x plus 2. Well, obviously, there's a very conspicuous factor that we are off by. 18x plus 6 compared to 6x plus 2. 18x plus 6, 6x plus 2. Think about for a second, maybe hit pause. Clearly, that is triple that. And we've made a pretty big, like I said, a conspicuous ignorance here by we've ignored that 3. We just said, you know what, man, just pretend that's not even there. 2 times stuff to the first, done. Well, the problem is we forgot that the function isn't just some random thing being squared. It's not just x squared. It's some other thing being squared. And that other thing has changes, rates of change that are associated with it. So we have to think to ourselves, okay, a square causes a function to change like this, but also this thing, this linear function, changes by a factor of 3. And now when you multiply this out, you, instead of getting this 6x plus 2, you get the proper 18x plus 6. If you multiply all that out, you'll see. Okay, so now let's figure out how we can phrase that, put it into notation. First thing is, let's just, well, I'll leave that stuff up there in case we need it. Let's think of the original function. So I'm going to rewrite the original function as y is equal to u squared. And the derivative of u squared is clearly 2u, unless we are finding the derivative with respect to x. And that's what we're doing here. So for example, dy du would be 2u. dy du again would be 2u. But what we are in search of is dy dx. And And in dy dx, we can't just take the derivative with respect to u and call it a day. So the general form of this, the general form, and I'll talk about that in a second, the general form would be dy dx is equal to dy du times du dx. And you can clearly see, oh, I can multiply, I can divide those du, and yeah, that's fine. And you'll get dy dx. In this particular problem, u squared, I put a u in there saying, you know what, I don't want to deal with this 3x plus 1, I just want to kind of ignore it. The derivative of y with respect to x, you'd think, oh, that's just 2u. But we've ignored the fact, we've entirely ignored the fact that u might have x as part of its calculation. So we now need to multiply this by du dx. Okay? And that's where this 3 came in. This 3 said, hey, man, I think you ignored the fact that this was a linear function being squared. So you have to worry about its rate of change too. So in this problem, it would be like 2 3x plus 1s, because that's what u was, to the first, right? To the first, times however much u changes with respect to x, and that's 3. So that's just an argument about why the chain rule works, and I'm going to pause and resume with another video in a second.